In this video, I will talk about time series ARIMA models in Stata. Before you watch this video, please make sure that you have watched my other two videos called Time Series ARIMA Models and Time Series ARIMA Models Example. So I have opened here the program in Stata and I have executed it. If you would like to get a copy of the program as well as the data and the handouts, please go to the website. The link is below the video, and once you're on the website you will see the other videos and a lot more information on this topic. So I have some data here on PPI, the Producer Price Index, and I'm filing a file right here with this command, which is a Stata file, and then I'm defining a few variables. My dependent variable Y list would be PPI, the Price Producer Index, the Producer Price Index, and I will also define a difference dependent variable, which is basically D of PPI. This is the difference operator in Stata. And I will also define the time variable, which is T in the data set. And also for some of the graphs, I need to define how many lags I need, and I'm defining this as 40. So when you are using this program, all you need to do is change the data set here and the variable names, and the rest of the program should work with your data. So the first thing to do in Stata is you can describe and summarize the data, and here are the results. Using describe, we have time in quarters and the producer price index since the dependent variable. So now we have 169 observations, and the mean for PPI is 664. Okay, the next thing that you can do is set the data as time series, and you use tset, and then you put the time variable in there, and here it's telling you that it's recognizing the T variable, and this is the second quarter of 1960 and to the second quarter of 2002, and the delta is 1 quarter in increments. Okay, alternatively you can use tset, and you could say time comma quarterly and then generate a time variable here, but I do this using the standard Stata commands. Okay, the next thing you can do is plot the data. Okay, so you can do this in two different ways. You can use the time series commands, which is two-way, and then you put TS line and you just put the Y list. Now notice this is the dependent variable that we're using, and for me this is the PPI in this example. Or you can execute this line, which is two-way line, and you could put the Y list and time, which is the standard way to just plot two variables once against each other. So I'm going to use the Stata commands that use the time series definition of the data. So if I execute this line, you will see this graph right here. I've already executed the whole program, so I'm just going to open graphs that I've already have open here. This is the first graph that you will see. So you can see the data. This is the time, and this is the variable PPI, and you see that the variable does not look stationary, has very strong trend. And the next thing that you can do is that you can execute the TS line for the difference D of Y list variable, and this graph is right here. So the difference variable, you can see how it's more it doesn't have a trend, but it does have an increased variance. So we will be using this variable as a preferred variable for the rest of the program. So now the next thing that you could do is do the Dickey-Fuller test for the variable to just formally test for stationarity. And the command for that is dfuller, and here you have the Y list, that's your dependent variable. you put here drift, regress, and legs equal 0. So these are some standard commands here. And this is the outcome that we have here. We're using this regression. We have 0 legs on the dependent variable in addition to just the variable. So what's the Dickey-Fuller test? The dependent variable is delta yt, and the independent variable is the first leg of yt, which is yt minus 1. And this is the coefficient that we need to look at. And we're seeing that this coefficient, this is the t-statistic, and that t-statistic is basically not significantly. The null hypothesis that this coefficient is not significantly different from 0 cannot be rejected. So actually that's bad news, since it means we have non-stationarity here, and we would need to difference the variable. Now what Dickey-Fuller test is doing, here I have the same command right here executed in a slower way, which is you're regressing the difference dependent variable on the lagged variable. And so you see like how these results right here are absolutely identical to those, because that's what the Dickey-Fuller test is doing. So again, there's no need to do both, because it's the same thing on this line. Now for the next test, you can do a Dickey-Fuller test where you can also include a trend, and you can have the trend right here. You see, instead of drift you say trend, and here's a trend variable. And again, you can see that this coefficient, unfortunately, again, is not significantly different than 0. That test statistic minus 0.79 it shows that it's not significantly different than 0. Therefore, again, we have non-stationarity. Okay. The next thing that you can do here is you can include more legs on the dependent variable if you want to. I have not executed this here. So in the next command, you're doing a Dickey-Fuller test now on the differenced variable. You see it here. Instead of the original variable, you're using the differenced variable. And so if you look at the results, you see how the dependent variable now, it's a second difference, because the basic Dickey-Fuller includes the first difference, so this is now a second difference, and this is the lagged difference variable here. So that's the coefficient, and this is the test statistic of minus 6.86, which actually indicates significance. So that's a good thing, because significance means we now have stationarity in the differenced variable, and this means we need to use a differenced variable. So I have used another one, regress, and this is the differenced variable, and this is the lag difference variable. And again, this is equivalent to the results above, as you can tell, only that I did not want this to be a black box for you, and I wanted you to know which regression is run here. Okay, so again, the conclusion of the Dickey-Fuller test is that we would need to be using the difference variable, because we have now stationarity for it. Okay, next thing that we will do is correlograms and the ACF and PACF. And to do the correlogram, you use corregram, and you put the dependent variable y list, and it comes out like that. And I copied and pasted this in the handout, the example handout, and you can see the legs. These are the legs on the dependent variable. This is the ACF, and this is the PACF. And again, you see very, very slow decay in the original variable, and which indicates non-stationarity. And here you have a very strong first lag, and then everything else is kind of died off. So so you can actually see here It's it is like an ACF, only that it's like horizontal, not vertical. And you can see a very strong first leg and then almost nothing afterward. So the next thing that you can do is look at the ACF and PACF, and I'm just gonna open up the those graphs. So this is the ACF graph, and again you see it's very, very slow decay, which indicates non-stationarity. And the PACF graph that you could get after you execute this code here is this one here. Okay, and again you see a very strong first leg, maybe a second one, and then it just cuts off after that. So this again, not much afterward. So the conclusion from that is, because of the ACF, we also shouldn't be using the original variable because it's not stationary. Okay, so now we can do the parallelogram on the difference variable, and you put the d.y list, and here you have the results. This is the ACF. Looks like it's kind of tailing off very nicely, and here you look at PACF, very strong first leg and nothing afterwards. So you see a nice decay here, very strong first leg, nothing after it. So this maybe indicates an AR process. So let's look at this, the ACF, if you execute this. Okay, so we see a very nice tailing off of the ACF here. And then if we look at the PACF, this is what we will get. This is the PACF. So you see a very strong first leg, and then these are not very significant, just barely out of the significance level, but much smaller in magnitude. So what this tells me is that probably we have an AR1 process, is my conclusion from this. Okay, so now that we have looked at the ACF and PACF, we can estimate a few ARIMA models. So here's the models that we're estimating, and for ARIMA models, the first number indicates the number of legs on the AR, then this is the number of differences for the variable, and this is the number of legs on the MA component. So when we have a 1, 0, 0, this is a 0 for no differencing, and here we have an AR1 process. So the command for that is ARIMA of Y list, this dependent variable comma, and then you put the ARIMA here. And this is the results here. You have a leg, the first leg. This is a 0.99, very significant. And so one thing you see is that, again, if you're looking at the non-difference variable, it's not stationary because that coefficient is very close to 1. Okay, next we can estimate an ARIMA 200, or which is the same as AR2, and these are the results. You have two legs now that are both significant. Next one, you can estimate an MA1 model. Again, these are the results. And here is where you can estimate an ARMA 1-1 model. And you can put in there both coefficients on the AR and MA process. Again, I'm just doing this for the exercise because we actually don't have stationarity in the original variable, therefore we shouldn't be using it. See how this coefficient is very close to 1. Okay, so next what we can do is we can do an ARIMA model, which is on the difference variable. And the reason why we know it's difference is that the middle one here, D, is equal to 1. Okay? And you can either do it that way with here, or you can do an ARIMA on D dot the original variable and then put the 0 here. which is the same thing. You either specify it here or you can specify it here. So this is, the first one is an ARIMA 110. So these are the results. You see like how the dependent variable is the difference here, and then this is the first lag of the variable here. So we have also significance here. Okay, then we have an ARIMA 011, which is only having the MA component, and it's significant. I wouldn't go with the model though that doesn't have an AR component to it, given what we saw in the ACF and PACF. And here is an ARIMA model that has one lag on AR and one lag on MA, and that's actually a fairly good model. So this is the coefficients that you can copy in the table in your paper, and you can also put not only the coefficients but the significance. Okay, so that's a pretty good fitting model. And so let's go ahead and estimate a few more. Here we have an ARIMA 113, and you can see 3 lags on the MA component, and they're just this one, you know, barely significant now. So I don't know if we need to go with that many components. And here is, we have another ARIMA model that is a 213. Here we have 2 lags on the AR and 3 lags on the MA. And here we have pretty good significance on the first and the third one, and these are, both of them are significant. So based on that, I also like this model here that we have. So if it were up to me, I would go with the ARIMA 111 or the 213 based on the significance of the coefficients, and something else that we are going to talk about here about the model fit. But before that, again, if you want to, instead of putting lags like that, all the lags up to 3, you can put lags the way you want to. If you just execute ARIMA on the difference variable, and you could put AR and you could put the which lags exactly you want. So you may put 1, 2, and 7, and none of them in between. Or you can put from 1 to 2 or from 1 to 3. Or if you just want to select which ones you want, you can put them there. So you can use this kind of function with seasonality. Okay, so the next thing to do is the AIC and BIC for model fit. And you can estimate the model, and I'm going to estimate these two, re-estimate them from above, and then calculate the these AIC and BIC criteria. So this is what we've seen before, and these are the AIC and BIC criteria. So we're basically comparing the 393 and 405 to this one, to the 390 and 412. So they're very, very similar to each other, and that's why I'm saying is that I would probably go with the more parsimonious model, because it just has 2 parameters, they're significant. You can also go with this model because virtually, well, we have this lag is significant and this one is significant, and the model fit is pretty good as well. Okay, so the next thing that we can do is I will show you how to do detrending. Okay, and you can regress the original variable on a time, and this is the result, and you can predict the residuals. Now the residuals is basically the variable that is detrended. Okay, and so now that you have this, you can plot two-way line, and you can plot those residuals, ET coming from the detrending against time. Okay, so this is what we have here when we have the variable detrended. So again, it doesn't look, it looks like a lot of swings in here. Okay, then you can do a Dickey-Fuller test to check for stationarity. And here we have now the Dickey-Fuller test on the residuals right here. And one conclusion is that, yeah, again, you see like how we have the coefficient, and that is the test statistic, which indicates that the coefficient is not significantly different from 0, which means we have non-stationarity. And you can also look at the ACF right here and the PACF of the detrended variable. And this is what we get here. You see a very, very slow decay, again, indicating non-stationarity. And here the PACF looks like that, with strong first and second leg, and not much other than that. Okay, so this was my example in Stata on how to do time series ARIMA models. Thank you for watching.